The only announcement I know about is the one about the students interested in a biopharma manufacturing careers. There's a 1-week summer opportunity for them. The students are paid $1,000 for that 1 week, and travel expenses are covered. So it's a good deal. I have the website and also the the fact that the application deadline is in January, but I don't know when in January, so that's not very helpful. Except the website's there, and you can find out that information there. And Bill's the only one here, but I'm glad you're here. I can hardly talk. Started clogging up late in the last class, and now not getting any better. Oh, and now we double the class size. All right. Josh is here. Okay. By my checking on things, I don't believe example 5, that where we are is chapter 13, functions of several variables, 13.7, tangent planes and normal lines, and page 935, example 5, but that's not, well, I thought for certain I hit that button, but evidently it didn't take. Okay. And evidently example 5 is not in the slideshow, so we'll get it from the example 2 slide. I think that we had to use this one for 3, 4, and 5. Whoa, let me get my pen set up. Okay. All right. Oh, it's coming up now. Any questions before we get started today? No questions or anything. Good. Example 5, top of page 935, says, is finding an equation of a tangent line to a curve. Find a set of parametric equations for the tangent line to the curve of intersection of the ellipsoid x squared plus 2y squared plus 2z squared is equal to 20. Okay, please don't ask me to draw this. That is centered at the origin, by the way. And the paraboloid, which is x squared plus y squared plus z is equal to 4. Okay. Now, there's just a little something about this drawing that doesn't quite ring true to me. Oh, no, got it. Okay. I think it's okay. Well, number one, that's a 20 and not a 200. So that doesn't ring too true, since I copied the problem wrong. But to get this to look more like what I was anticipating to see from the slide here, I would divide everything by 20 on that top one, and that would be x squared over sorry, I can't talk. The square root of 20 is 2 root 5, I believe it is. Okay? Plus y squared over square root of 10 is, I'm sorry?
Can't we just subtract 20? To make it equal to 0?
Not to equal 0, I want to equal to 1.
Oh, sorry.
Yeah, yeah, that's sort of the standard form for it. Yeah. Okay. Plus z squared over root 10. and that would equal 1. Okay. Now that's why I said it was centered at the origin, but when I just glanced at it, I didn't notice the 20 out there. I was thinking that was 1. I said, this is going to be way too small. But this is a number close to or more than 4. This is a number more than 3. Ooh, did I say that right? Yeah. This is more than 4, this is more than 3, and that's more than 3. And the Z one was the one I was looking at. Yeah, that's looking like it makes sense. Well, everything except the y-axis. It looks like it's bulging out too far on y. The x and the y should be the same, and looks like it intersects the x-axis at just less than 5. And the y-axis should be much less than, okay. I can't see any way they've got this quite drawn correctly. It should be an ellipsoid whose long axis is the x-axis and the shorter axes are the y and z. And this, the way they've got it drawn here, looks like y is longer, x is next long, and then z is the shortest, which, I don't know. Maybe it's just my perspective on it. But that's beside the point. Okay? Find the set of parametric equations for the tangent line of the curve of intersection of this ellipsoid and that paraboloid. Now, also, if I'm not mistaken, there'll be 2 curves of intersection. I don't see any way this paraboloid could be sitting in the middle of this ellipsoid, and they show the intersection at the top. They don't show the intersection at the bottom. There's got to be a second intersection down there. But they're not talking about that. Oh, I didn't read far enough. At the point 0, 1, 3. Okay, now, that's beginning to at least make a little more sense. Well, let me write it all down. At 0, 1, 3. Now let's see, because I'm such a skeptic, let's make sure this works. When x equals 0, this is 0. When y is equal to 1, this is 2. And when z is equal to 3, this is 18. 18 and 2 is 20. That fits fine. How about down here? 0 plus 1 plus 3 is 4. Yeah, that works perfectly fine too. So I'm convinced 0, 1, 3 is on that point of intersection. Okay. Now, and in my mind, this has to be an ellipse up there too, and it sure looks like to me the way they've drawn it is a circle, but that may be just my perspective. Okay.
So I thought we were supposed to make it equal to 0 to find the
Oh, okay, you're trying to find the points of intersection, or the
equation of the tangent line. Maybe
okay. Okay, we got to get there, but you see, we first have to find, in my mind, the equation of the curve that tangent line is on. So,
oh, okay.
Yeah, and yeah, so that's why I'm checking out the things here and say that curve, in my mind, has to be an ellipse. Okay, so let's see. Okay, All right. Now, do we actually have to solve that? No, and I see what you're saying. Okay. For this one, they're calling this the function f, and that way we are subtracting 20 from both sides. I see what you're getting at now. This is f of x, y, and z. This is following up from what we were doing last time.
Yeah, that's what I was saying.
Yeah. Let's go back just to refresh. The equation of a tangent plane, which is not what we're doing. We're doing an equation of a tangent line.
Oh.
But yeah, we still got to get there. Well, wait, not quite, but it has to be a line in the tangent plane to both of them. So yeah, we will get there. So we are doing this. If f is differentiable at some point, then the equation of the tangent plane to the surface given by this. So we have to write it in that form, which is, I think, what you were saying. At that point is, and then here's the thing we do with that. Okay? So, obviously, we've got to take the partial of f with this. Well, we first got to write down what f is. Then we got to do the part, well, okay. The easy way to go is what's above there, that the gradient of f at that point dotted with v. Now, what in the world is your v? V is the vector which is going to be our tangent line. Okay, so that's what we're going to have. This is going to be an x, y, z. That's all it's going to be. But that tangent line has to touch at that point, so yeah, we've got this. So let's first, then, I see what you're saying now. I was just rewriting this so I could have make sure that everything was looking right. I still don't think the graph looks right, but that's beside the point. Let's just do this. This f of x, y, z will be x squared plus 2y squared plus 2z squared minus 20. Now, when you take the gradient of this, there would be a gradient of the same function we had before, because the 20 isn't going to contribute a thing. But we'll do that. At the same time, let's identify the g of x, y, and z as being this one, x squared plus y squared plus z minus 4 equals 0. Okay? Now, and I think what you were suggesting is now take the gradient of this, and what do you get? Yuck. It was supposed to be an equal sign, and it became out of parentheses. I don't know how. Okay. Gradient of f is 2x plus 4, wait, 2xi plus 4yj 4z k. Okay. You got me writing a square. Right, yeah, all right. Okay, okay. All right, that's a little bit better. All right, and we also need to evaluate this at our point. So let's see what the gradient of f is at 0, 1, 3. For j, 12k. Okay, let's do, in some sense, the same type thing for g. What's the gradient of g? 2xi 2yj plus k. Okay, and we want to evaluate that one, and this is a vector. I forgot to put, yeah, at 0, 1, 3. Goodness gracious. And what would that be? 2J
Plus K.
plus K. That 3 doesn't have anything to do with it. Yeah. Plus K. Okay. Okay. So far, so good. Now, the gradient of F is direction of, and at this point here, is the direction of kind of like a derivative there. I mean, that's sort of like it is. So that, okay. And the gradient here is going to be also a tangent line. It's not a tangent line. You don't have enough for it, but the vector in the direction of a tangent line there. Okay. So each of these. Now, okay. Let me rephrase that a little bit. One is the direction, this is the one on the ellipsoid, the direction of maximum increase at that value, right, okay, at this thing, that would be the vector, that would be maximum increase here. That would be the vector of maximum increase there. Now, those two, whatever they are, this is along that plane, this is along this plane. The cross product of those, that's what they're going to do next, of those two gradients is a vector that is tangent to both surfaces at that point. Okay? It's...
How is that possible, though, from what they're drawing?
Yeah.
I just can't see it.
Okay.
A tangent line that would make sense on both of them.
Right.
Unless it's just in that crease or something where they're connecting.
Yeah. Well, let's see if I can.
One's like a little egg shape. So
Yeah. Okay. Let's see. The tangent. The tangent line that's in maximum increase, let's take, you see, you can't see this here. There's not much increase there, okay? 4J would be in this direction, and 12K in that direction. Now, that, see if I can get this up here. That doesn't quite seem reasonable here. 4J is out this way, and 12K is up that way, okay? So this would be that would be coming out of this normal to, okay. Oh, the last guy I knew had a ball, okay. And he took it with him, okay. This, because it's getting where it's flattening out, this is almost straight up. It's not quite. So it's going to have a large K component there. And this is over here. Now, the X, you see there's no variation in X here at all because you're at the point 0, 0 on X. So it's not increasing or decreasing anywhere on X. It's flat, okay, or parallel to the X-axis, okay. So this is something going, it is coming out on the Y pretty significantly, but really up on X. This is the direction of increase of that. Now, if you do the same with the parabola, if I could hold this up here, the parabola, it's 2j, positive this way. So this is a line pointing out from normal to, out from the, that point on the parabola. So 2j, the parabola is, the ellipse is more rounded here, so it seems like that would be a smaller number, but, oh, this is better, okay. This is rounded, so this, but then the k part here is just a slight increase in k. So it's again in the j direction, okay, 2 in the j direction, and only 1 in the k direction. So it's just coming out perpendicular to that surface there. So if this one's perpendicular to that surface, this is perpendicular to that surface, the cross product would then have to be the line that's tangent to both of them, okay? And that's sort of what you got there. Now, notice here, there's no, again, variation in x, so we're not expecting one. Let's see what we do. Let's first do the cross product. We've determined this, let's do the cross product. It's a vector tangent to both surfaces at that point. So, we'll do our I, J, K, I, J, and we'll do 0, goodness gracious, get out of there, 4, 12, 0, 4, and 0, 2, 1, 0, 2. Okay? That's our determinant, you might say. Let's do the down diagonal here. What does that give you? 4i. Okay. This one gives you 0. This one gives you 0. Okay. Then do our up diagonals. Let me erase the down so it won't be quite as ugly here. Still be pretty ugly, but get out of there. Okay. Up diagonal will be 0k plus 24i. Yeah, you're minus, you're right. Okay. Okay. Minus 24i. And, okay, so again, so we got minus 20i. If I could get that to right. Okay. So, everything is in the I direction. Now, why minus 20i, I'm not really sure, but yeah. But that's what your cross product is. Okay? Okay. So the tangent line to the curve of those two surfaces at that point is a line that is parallel to the x-axis, because this only has x coordinates here, and passes through the point 0, 1, 3. Okay? And the direction numbers, because that's the only vector, and I don't know why they do this, but they say this can be written as 20 minus 20i plus 0j plus 0k. Okay. Now, that gives them these as your direction numbers. That's the only reason they wrote it that way, so you could see those as their direction numbers. Now, there's a set of parametric equations for the tangent line. If you remember direction numbers before, what did we do with them? We put them in the last example. Example 4, you put them in the denominators. Can't do that here, okay? 0 and 0 don't fit in the denominators too well, okay? So the set of parametric equations for the tangent line passing through that is okay, what we would have, oh no, I'm sorry. The normal line has that. I'm sorry, I was looking at normal line. So the set of parametric equations for the tangent line passing through that point is there's my point. I couldn't find my point here. You have x minus 0, okay, that is in the direction of this one. This will be y minus 1 would be that one, and z minus 3 would be that one, except you have the point the y is 0 and the z is 0. And now that's a 3, that's not a thing, so this thing keeps popping up there and it drives me nuts. What you're doing is the line that if you go back to, I believe it was chapter 11, is where we did the lines. I had it marked here. Yeah. The parametric equations for a line in space, these are your A, B, and C, okay? And if you look on page 787, that theorem sort of in the middle of the page there, you say x minus 0, because that's your x1 here, over, I'm sorry, I'm looking at the wrong one. That's what I wanted, but let me get it written correctly. X is equal to 0 plus AT, well that's here a minus 20t, okay, which don't really worry about that yet. Y is equal to 1 plus 0t, and Z is equal to 3 plus 0t. You know, plugging in the A, B, and C in that theorem 1111. Okay? Now, there's absolutely no reason for a minus 20. I mean, this basically reduces just to x equal t and y equal 1, because 0 times t, and z equal 3. That's how they came up. Mine don't stack up too well because my pen's so slow. And those are your parametric equations for the tangent line that passes through that point. Where did all that math come from? Okay. These are the parametric equations using the point here as the x0, y0, z0, and then your direction numbers as your coefficients here. Well, if you wanted that as a unit vector, you just divide by 20, okay? The sign doesn't really matter here either because it's going both directions, so just keep it general and since I did write it, let me write it correctly. That is just a minus there, yeah. So you don't need the 20 or the minus 20. Just x is in the t direction. That means it's parallel to the x-axis, and y and z, that's just the point where they intersect, and the t is going infinitely large in this direction and that direction. Paralleling the x-axis is all it is. You don't need the minus 20 there at all. It's just x is that way and this way, and you can put any value in there. The t, that's your parameter. So the y and z, you're at the point y is equal to 1, z is equal to 3. So that gives you that. Then it's parallel to the x-axis. Well, parallel to the x-axis like that. Okay. They skip an awful lot of steps. Okay.
Yeah, let's go straight to
Now, that thing about the direction numbers, what they basically did is reduce it to simplest terms. Your direction vector, you could say, was minus 20i plus 0j plus 0k. You don't need a plus or a minus sign there just to distinguish from the others. Those are 0, and you could divide everything by minus 20, and you get I plus 0j plus 0k. So your direction number is basically just 1. They don't ever say that you need to reduce those to simplest terms. It just makes it easier to do that, okay? Because the direction vector is just a vector in that direction. And just write it in the simplest way. That would be just I. So, a lot to be desired there, I think. Okay. All right, let's move on to, sorry about that. Well, I'll get there in a minute. There it is. The angle of inclination of a plane. All right. Another use of the gradient, besides these others we've been doing, delta, or del f, gradient of f of x, y, z, is to determine the angle of inclination of the tangent plane to a surface. Okay? The angle of inclination of a plane is defined as the angle, always an acute angle, between 0 and pi halves. Okay? Don't have any obtuse angles, don't have any negative angles, don't have any weird angles, just the acute angle between a given plane and the xy plane. Okay, so here's the xy plane down here. Angle of any other plane relative to that. Okay? The angle of inclination of a horizontal plane, of course, would then be 0, because it would be noted. Okay. Now, here's the deal here. The angle between this plane and that plane is the same as the angle between their normal lines. The normal line to that plane, of course, is the k-axis. Normal line to this one is n. And if this is angle theta, that's also angle theta. Again, always a positive angle. So it doesn't matter which one you draw from, just make sure it's positive. Okay? If this had been a plane down here, then it would have been the same angle theta. If that was the same thing here, you would do the same theta. So there's the angle of inclination. You come over here and do that angle. Works the same. Okay. Now, because the vector k is normal to the xy plane, of course, you can use the formula for the cosine of the angle between two planes to conclude that the angle of inclination of a plane with the normal vector n is then this. Now, when it says use the formula for the cosine of an angle, okay, between two planes. Don't know if you remember this, but this comes from our dot product equation. That the dot product of any two vectors is equal to the magnitude of one times the magnitude of the other times the cosine of the angle theta. So just take that, divide it by magnitudes of the two normal vectors there, okay, and that gives you the cosine of the angle. Well, what's the magnitude of k? 1, because that's the unit vector in this direction. So this is then just the magnitude, and remember, we're only doing positive angles, so that's why absolute value is here. The dot product here could come up negative. We don't want a negative. We want the acute angle. So we're going to use the first quadrant angle magnitude of the dot product is going to be positive. N dot k divided by magnitude of n. Okay. And that is another way we use the gradient. Well, wait, you may say, where does the gradient come into this? Okay, I don't see a gradient anywhere in that formula. Okay, well, I guess example 6 is going to show us that. Find the angle of inclination of the tangent plane to the ellipsoid. And this ellipsoid, they've written in standard form now. You could have written that x squared plus y squared plus 4z squared is equal to 12. That would have been like the last ellipsoid we had. At the point 2, 2, 1. Well, pardon me, but I've got to check and make sure this works. 4 over 12 is 1/3, and 4 over 12 is 1/3, and 1 over 3 is 1/3. They add the 1. Yes, that works. Okay, that point is on that ellipsoid. Okay, plenty of other points there, but that's one. Find the angle of inclination of the tangent plane to the ellipsoid. Okay, now go back. The equation of the tangent plane was that one that we were referring to earlier. By mistake, it wasn't really the one we wanted. 1313, bottom of page 932. Okay? So, we'll get to that if we need it. So, and again, it doesn't really make a lot of sense, but they say do it, so let's do it. Let's come up with the function f, which is a function of x, y, and z, which is equal to 0. And what would that be? X squared over 12 plus y squared over 12 plus z squared over 3 minus 1 equals 0. Now, frankly, I would have been just as happy to have had x squared plus y squared plus 4z squared is equal to 12. That would have worked a lot smoother than this, but they're the same functions. They just vary by a factor. And what are we going to do for it with it next? Take the gradient. And what would that be? Okay, you wrote it that way? Okay, yeah, x squared, x over 6i. Y over 6j, right? Plus 2/3 z k. Right? Okay? Now, at the point, the gradient of f at 2, 2, 1 that we have verified is on the thing, that would be what? Get out of there. Okay, 1/3 I, 1/3 j. I can't read my own writing. That is a 1. Okay. 2/3 k. All right. Okay. All right. So there's the gradient. Now, the gradient is in the same direction of the is normal to the tangent plane. So that's your normal. That is what earlier we were calling n. Okay? Now, having said that, what is the cosine of the angle? That's what we're looking for. Find the angle of inclination between of the tangent plane to the ellipsoid at that point. So cosine of theta would equal, what are we going to have to do that with?
So gradient of change.
Yeah, it's the gradient of this dotted with the dot product, I can't talk, of this 1/3 I plus 1/3 J plus 2/3 K, dot that with K, right? Well, guess what? This is always going, it doesn't matter what the first two are, this is always just going to be the product of those two coefficients, okay? Over, and we just need the magnitude of this one. So let's do that. Magnitude of n. One-third squared plus 1/3 squared plus 2/3 squared. Yes, I ought to put those in parentheses. Okay, so it's going to be a 3 in the denominator, and you have 1 plus 1 plus 4, that would be the square root of 5/3. Is that right? That's 6. Square root of 6/3. I'm sorry, I can't add. 4 plus, yeah, square root of 6/3. Oops, wrong thing. Okay. Square root of 6/3. Okay? All right. So what is this going to be? This dot product, that times 0, that times 0, this is 2/3 over the square root of 6/3. You can multiply by 3/3, and those go away, and you have 2/√6. Okay? Now, root 6 obviously is a number bigger than 2, okay? Which is good, because cosines have to be, between 0 and 1 to be in the first quadrant, okay? So that's good. So 2 divided by root 6, and then do an inverse cosine of it. What do you get? It's not one of the ones I know off the top. Black boxes take a while, don't they? Whoa! Yeah, wait. Let's see. Is that the same as the square root of 2/3? I've got to check that out.
is 35.263
Second.
degrees.
What's that again?
The answer I got after doing the,
Right. 35.3?
yeah, I got 35.264.
Okay. We'll round it 35.3. I don't know why they use 3 digits. Is that right? I've got a...
It is, because that's what I...
Yeah, but I mean, square root of 6 over 3, is that the same as... Oh, I'm sorry. No. I mean, 2 over root 6. Yeah, if you multiply this by root 6 and this by root 6, you get 2 root 6 over 6. And that's root 6 over 3. Yeah. Well, wait. How do they get the square root of 2/3 out of that? Okay.
It's because when they did the bottom...
Oh, okay. This is the square root of 2, square root of 3 over the square root of 3 times the square root of 3. And that goes to 1, so it's the square root of 2/3. Yeah. Got it. Yeah, it is the same. First I went, whoa, where did that come from? All right. So that would be about 35 degrees or so. Which is almost, if my memory's right, no, it isn't. I was going to say it relates to a radian, but it isn't. That's 53. Okay. Special case for the procedure shown in example 6 is worth noting. The angle of inclination theta of the tangent plane to the surface z is equal to f of xy at x0, y0, z0 is the cosine is equal to 1 over the square root of f sub x squared plus y sub x squared plus 1. All right, I guess I'll take the word for it. They do nothing but just say that's what it is. So, all right. Well, let's just see how they work the problem. Maybe they'll show how they did that. I have a feeling they just skip a lot of steps and say this is the answer. Begin by letting f of x equal that, which we did, and then take the gradient of that at 221, and that would be exactly, there's the gradient of that, and then at 221, that would be the gradient at that point. Because the gradient is normal to the tangent plane, and k is normal to the xy plane, it follows that the angle of inclination, which to me, it's doing a dot product with k only gives you that component times k. So, I mean, it's times 1. So, that's seems a little ridiculous to write it all down. Divided by the magnitude of the gradient there, and that would be 2/3 over that thing, which we did, and they just come up with that being the square root of 2/3, which is true. We verified that, okay? And then the arc cosine of that is 35.3 degrees, just like you saw. And okay. Whoops. This is sort of interesting, too, the way they did it. I'm going to point this out to you. Sorry. If you write the equation like this, okay, and And that's this gives you when x equals 6 and y and z are both 0, then that's no, that didn't work either. I thought it was just happenstance, I guess it was, that these 3 points here, 6, 0, 0, 0, 6, 0, and 0, 3, 0 just happen to be the points of intersection of that tangent plane. I was just trying to see why that's the case here, and frankly, I can't see it. There's nothing that relates that to me. Now, the other thing that gets to me here, this is supposed to be at the point 2, 2, 1. It seems like you're coming out 2 on x, going over 2 on y, and then going up 1. I guess that's pretty close, but it just, yeah, I guess that's something about 1. That somehow looks like that shouldn't be on the surface, but again, it's hard to get any perspective here in this. And how that turns out to be going through those 3 points there, I'm not sure I see why that's the case, but I'll have to take the word for it. It is. But I was trying to figure that out, but I can't see an easy way to do that. All right, never mind. That was just a little brain thing I wanted to do. Okay. And then the last little subsection here is a comparison of the gradients of delta xy, gradient of alpha of xy, and gradient of capital Alpha of xyz. Okay? All right. This section includes with a comparison of these two. Now, this is the gradient of a two-dimensional function. Alpha is a two-dimensional function here, and this is a three-dimensional function. Now, we know that the gradient of a function alpha of two variables is normal to the level curves of alpha, and we talked about that too. The gradient is always going to be perpendicular to your level curve. That's just how it is. Specifically, Theorem 1312, that was down here, states that if alpha is differentiable at x0, y0, and the gradient of alpha at that point is not equal to 0, okay, that's a 0 vector because that's a gradient, then the gradient of alpha xy0 is normal to the level curve through x0, y0. Now, if alpha is differentiable at x0, y0, that just says the same thing this does. So what's the point? And they're really not making a very good, unless they do that after this, how is that making a comparison here? Well, what we know here is the gradient is normal to the surface there. This is normal to the curve. This is normal to the surface. So I guess that's the comparison they're making, but I just don't see them making a very strong case for it. Having developed normal lines to surfaces, we can now extend this result to a function of three variables. Oh, I see. I'm sorry. I was looking, I thought they had the numbering wrong, but they were referring back to Theorem 1312, which came several pages before, in fact, sections before. Yeah, that was at page 926 in section 13.6. So having developed normal lines to surfaces, we can now extend that result to the function of three variable. The gradient is normal to the level surfaces. If f is differentiable at that point, then the gradient of f not equal to 0 at that point, then the gradient of f is normal to the level surface through x0, y0, z0. Okay, and that's what we were seeing before. The gradient is pointing normal to the surface, whereas in 2 dimensions, that's when I was saying it wrong. The gradient in 2 dimensions is pointing to the line direction of steepest increase. Not necessarily here. Now, what that was normal to the contour line, okay, and this is normal to what you might say is a contour surface, which means perpendicular to it. So that was the connection. I was saying it wrong to say this is in the direction of maximum increase. No, it's normal, which would be maximum increase in 3 dimensions. That would be the normal line. Okay. So they said it better than I did. Okay. And that, I think, is the last slide here. So homework exercises here. Boy, is this not a good section to be through with. 3 or 5. They're both at Calc Chat. 5 is at Calc View. And I said this to my last class, and I'll say it to y'all too. I know I must be getting sort of nauseating, always saying that, but I had a student in my office. I'm his advisor. I've only met him once or twice before, but I had seen him Friday a week ago, was it? Yeah. And he came by my office last week, and he was sort of saying he was sort of struggling a little in trig, pre-calculus trig. Used the same book, same author. And he was, saying about, he not following the stuff well. I said, well, are you using Calc Chat and Calc View? He said, what are those? And I said, I picked up the book. No. I'm not. He's not in my class.
Oh, okay.
And I just couldn't believe there's an instructor that doesn't tell the students, you can get help for this stuff, Because I turned to the back of his book. It was pre-calculus, LarsonPrecalculus.com, CalcChat.com, and CalcView.com. I said, there they are. Those are 3 absolutely free websites. You don't need access codes, anything else. Go to them and get tutorial help, worked out solutions, And so that's why I say this every time. I thought I was just being really obnoxious with it, but the thing is, the help is there. And he had pre-calculus, algebra, and trig, same book, never even realized those sites were there. Okay, so I'm going to keep doing it, sorry. But do number 7, that's a Calc Chat and Calc View. Then any of the odds 9 through 15, they're all at Calc Chat. Any of the odds 17 to 25, all at Calc Chat, 19's at Calc View. 27 to 31, all at Calc Chat, 27's at Calc View. Now this is the new stuff we did today, and maybe 27 was too. 33 and or 35, both at Calc Chat, 33's at Calc View. And then 37 to 41, they're all at Calc Chat. 43's at Calc Chat, 45's at Calc Chat. You can explore doing 47 if you want to. That's at should be at Calc Chat. Then either any of the odds 49 through 53, no, 49 through 55, they should all be at Calc Chat. 57 should be at Calc Chat. Any of the odds 59 through 63 should be at Calc Chat. 63 is a proof, so only if you want to do that. Okay. Now, let's move on to 13.8. Okay. Well, let's just see for funsies. how long we got to go in 13. Yeah, we're not going to do all of 13, but we'll do 13.8 for sure. Let's just glance ahead. 13.8 is extrema. 13.9, great section, but we're just not going to have time for it. I'll try to do a quick slideshow of that, and same with 13.10. So let's get going on 13.8. This will be the last one you're responsible for on the test. So let's go to slideshow, current slide, and chapter 13 is still functions of several variables, and 13.8 is extrema of functions of two variables. Okay, we obviously are not going to do extrema functions of three variables. Thank you very much. Okay. So our objectives here are to find the absolute and relative extrema of a function of two variables. This will harken back to curves and things like this when you're doing max mins and absolute max and min. And we'll use the second partials test to find relative extrema of a function of two variables. We haven't had that yet, so that will be something new. So the absolute extrema and relative extrema. You realize extrema is the plural for extreme. So, consider the continuous function f of two variables defined on a closed bounded region R in the xy plane. The values f of AB and f of CD such that f of AB is always less than or equal to your f of xy, and that's always less than or equal to f of CD. Okay. For all xy's, the values f of AB and f of, CD are such that f of AB is always less than any of the other, less than or equal to f of xy, and f of xy is always less than or equal to f of CD. That would mean f of AB must be a minimum value and f of CD must be a maximum value. If all these are less than or equal to that one, and all your f of xy's are less than or equal to that one, and your f of AB's are always less than your f of xy, those must be the minimum and maximum values over this region. Okay? So, the requirement here is A, B, and C, D are in R. A is your x value, B is the corresponding y, C is the x, and D is the corresponding y. So, here happens to be a surface. And just by the way they've drawn this, these 4 points here at the corners are relative or absolute minima. There's 4 of them all at the same value, but only one up here that is a maximum. Okay? R contains the points on which f of xy is minimum and maximum points, which contains points, plural there, and this one's only a singular here for the maximum. If there was another up there at the same value, then it would be more than one maximum as well. Okay, that's just definition from a graphic point of view. Okay? A region in the plane is closed when it contains all of the boundary points. Okay, let's go back to this one. Obviously, these boundary points are included on the region because these corner points are boundary in two ways. They're included. So this is a closed bounded region R. Yeah, we see that. Okay. Now, a region is closed when it contains all of its boundary points. The extreme value theorem deals with a region in the plane that is both closed and bounded. Okay? In other words, it can't be a region that's taking off to infinity and never reaches there and just keeps going. It has to be bounded. The region in the plane is called bounded when it is a subregion of a closed disk in the area. region in the plane is called bounded when it is a subregion of a closed disk in the plane. Okay. Both of those statements are true, but it seems like they give the definition here after they said what you use it for there, but it just seems a little backwards, but okay. Theorem 1315, which you find on page 940 here, extreme value theorem. Let f be a continuous function of two variables, x and y. So xy plane down here, f is describing your z value up there. Now, I don't know why, every now and then you get these horizontal, vertical lines in there. They're not in the book, they're not anywhere else, I don't know where they come from. Let f be a continuous function of two variables, x and y, defined on a closed bounded region R in the xy plane. So you have the edges are, okay, closed, the edges are included, bounded means it doesn't just take off and go to infinity in any direction, okay, in the xy plane. There is at least one point in R at which f takes on a minimum value, okay? This is extreme value theorem. There's at least one point in R in which f takes on a maximum value. There may be more than one for the minimum, like we saw before, there were 4. The one we saw before only had one max, but you could have had double humps as long as they went to the same place. That would have been more than one max as well. But there will be always at least one that is a min and one that is max. Now, of course, since this is just a constant function, every point's a max and every point's a min. Yep. And you have all sorts of variations on that thing. A minimum is also called an absolute minimum when the maximum, and a maximum is called an absolute maximum. That's what we haven't been using the adjective absolute, but what we just described were absolute maximum. As in single variable calculus, there's a distinction made between the absolute extrema and relative extrema. Okay, and here's where that one comes. Definition of relative extrema. If f is a function defined on a region R containing x0, y0, the function f has a relative minimum at that value if f of xy is always greater than or equal to f of x0, y0. That would be this is greater than that, that would be the minimum. For all xy on an open disk, not a closed disk, open disk containing f of xy, x0, y0. Now what that means is none of your boundary values are going to be included in this. So the function has a relative minimum there, if that's true for everything in the open disk containing that. That will be a minimum in here. Maybe one of the boundary values may be less, but that doesn't matter. If you can draw an open disk that contains that point, and that be the minimum one, any size open disk, then that's a relative minimum. The function f has a relative maximum at that value if f of xy is always less than or equal to that f of x0, y0 for all xy in an open disk containing that point. So again, don't count the boundary values, boundary area, but this is the maximum. This is always greater than or equal to all those in the open disk. So again, your boundary values wouldn't contribute. Now, let's go back. I hesitate doing this. These then would not be classified as relative minimum. Okay? Those are minimum values, but you see you can't do an open disk that contains that point. Okay? And no other open disk you have, open disk will have something that's always less than. So on a relative basis, that's only your relative maximum right there. Okay? Because anything else you do, any other open disk that you do here, the minimum or maximum, except the one that contains that point, will be on the boundary. It's bizarre, but it's true. Okay. All right. I think we did all that. Yeah. Now, to say that f has a relative maximum at x0, y0 means that the point x0, y0, z0, which is the value at that, is at least as high as all nearby points. Oh, isn't that a weasel word? Nearby points on the graph of z is equal to f of xy. Similarly, f has a relative minimum at x0, y0 when x0, y0, z0 is at least as low as all nearby points on the graph. Okay? Now, that does look like a relative maximum there. Back in his hole here, the relative minimum, relative maximum here. Maybe a relative maximum here, it just can't be on the boundary. I just can't tell if that makes it or not. The relative min out of that hole and that hole, relative max here. It looks like a hole there, relative min. This one could be down here, or it may be here. If it's here, that's not counted. Okay, but it does look like there is something below that here and here, and maybe below it here too. Again, it's really hard to see in a perspective like this. But say relative extrema, you just have to pick them out. There's one, there's one, there's one, there's one, for sure. Looks like one there for sure. Oh wait, let me see. Yeah, there for sure. Can't tell if this is going to be, it looks like it is. One in there, one in there. So yeah, you can pick out this with relative.
On that picture.
Huh?
On that picture, is it possible to have more than one maximum relative maximum?
Relative, yeah. That's
That's
what they say, nearby points. Okay? If you take the nearby to be close enough here, yeah, then it's, now, actually, I can't tell, is this a continual line here? And if that's all at the same elevation, then all those would be relative maximum. But a relative minimum here, a relative minimum there. This one may be deeper than there, or this one, yeah, any of those, but they are relative because that nearby, that little weasel word there, make your disk small enough, and then that is the least value there. This is the greatest value for a disk here. Even if it has a whole bunch of them, still nothing is greater in any, yeah, so you can't have in this one lots of relative extrema. Absolute, only one, unless they all have exactly the same value. Like if this one, that one, that one, that one all had the same value, those would be absolute. But this looks like to me that's the absolute here, but none of the others get up that high, it looks like. I can't tell about this, I just can't tell there. Actually, it looks like it's getting higher over here, but I can't tell that. Oh no, that's just a Z axis sticking out there. I thought they had marked that as a maximum. That's just the Z axis coming through. So wherever the max value is here, could be there or back here somewhere. That would be your max. So yes, that's why they have a plural, relative extrema. Maxima and minima. Absolute, you can have more than one, but they have to have exactly the same value. Relative, they just have to be the greatest in their nearby frame. So anything around that one, around this one, yeah. Wherever the peaks and whatever the valleys are, if you could do a little open circle around that, that's the least value or the greatest value in that open circle. That's a relative max or min. Does the heat just come on? Suddenly here it's gotten hot, okay? It wasn't hot before, Were you going to say something?
What if it's not on the z-axis at all, or it's just,
Oh yeah,
if it's just flat on the z-axis?
They just drew the z-axis here. That wasn't necessary. I was thinking they had that marked as a relative extreme. I thought, and then I realized no, that's just the z-axis there.
But if the z is constant and x and y are moving in different ways,
okay.
maybe it would. I guess that would just be a straight flat plane.
That would be a plane that would cut this according to contours. You know, I don't know if that's what you're asking, but that would be it. At the very max of all those, that would be the only point on it. You go down and you might have a contour around here, a little bit further you have a contour here and here, you know. But then down here you have contours around single points there. When z is equal to a constant, then that gives you those contours and that very peaks and valleys. They will be inside those. They won't be circles, but closed curves. All right. To locate relative extrema of f, you can investigate the points at which the gradient of f is 0. Because if the gradient of f is 0, of the 0 vector, that means nothing. Now this, remember, is on a two-dimensional curve. The z is the third dimension, so your gradient of f would be 0. So in other words, you're at the peak, you can't go any higher in any direction, so your gradient is 0. Or the points at which one of the partial derivatives doesn't exist. Ooh, okay. That could also give you a max or a min, okay, the extreme values. Now, where does that come from?
But didn't we have that in Cal 2?
Yes. Or Cal 1, I was thinking it was. For extreme values or critical points, going to be doing the same thing, to even name them the same thing. Either where the first derivative is 0 or it doesn't exist. Only here it's where the gradient is 0 or the partial derivatives don't exist. See, before we only had one derivative, okay, so it's either where that was 0 or it didn't exist. Now it's where the gradient is 0, and that's a 0 vector, by the way, or one of the partial derivatives doesn't exist. So here's the definition of critical point, which basically is this way. F be defined on an open region R, that means not counting its boundary, containing x0, y0. The point x0, y0 is a critical point of f, of that function f, if one of the following is true. Okay. Now this is two-dimensional, two independent variables. L sub x of x0, y0 has to be 0, and L sub y of x0, y0 has to be 0. That means that is that would make your gradient the 0 vector. So it would be 0 I plus 0 j. 0. Okay. But the second is L sub x at x0, y0, or L sub y at x0, y0 does not exist. If either one of those does not exist, either one, then they both have to be for that to be 0, or one or the other, or both don't exist. Okay. So if f is differentiable, then del f, or the gradient of f at x0, y0, would be f sub x at x0, y0 plus f sub y at x0, y0. If f is differentiable, that was the key, then that gradient has to be 0. That would be 0, this is 0. Both have to be. Then every directional derivative at x0, y0 must be 0. No matter what direction you go, you must be 0. You're on the peak or a valley. I mean, absolute valley. And any direction you go must be 0. This implies the function has a horizontal tangent plane at that point, whether it's a max or a min, like here. Okay? Horizontal tangent plane x0, y0. Max or min. Okay? Relative maximum, relative minimum. And you could pick these out of that eggshell carton things that we were seeing before. min and the max. Okay? Because your tangent plane is zero slope in every direction. It appears that such a point is likely location of a relative extrema. I would say it is. This is confirmed by theorem 1316. Relative extrema occur only at critical points. Now, hang on to the thought for just a minute. If F has a relative extremum at x0, y0 on an open region R, then x0, y0 is a critical point of F. Okay? If F has a relative extrema at x0, y0 on some open region R, then x0, y0 is a critical point. Notice what they don't say. If it's a critical point, then it has a relative extrema. No, they don't say that. They say if it's a relative extrema there on open region, then x0, y0 has to be a critical point. So finding your critical points just give you candidates for extrema. They won't necessarily be extrema. But you can't have an extreme that's not at a critical point. That's a relative extreme. Absolute, yeah, you could. Relative, no. So let's do this one. Determine the relative extrema, and they say ma, as if there are more than one, of F. Ooh, goodness, I haven't been turning my pages. And this, you can also go to larsoncalculus.com for an interactive version of this type of example. Here's your f of xy is equal to 2x squared plus y squared plus 8x minus 6y plus 20. All right. Now, what might you do? Okay. Same difference, yeah. The gradient, yeah. Okay. Gradient and, okay, f of x, y. What would that be? 4x
plus 2y.
Okay. Let's do our i's first, yeah. Plus 8. Yep, that's your I. If we're from the south, that's your I. Okay. Okay. Plus 2y minus 6 j. Got it. Okay. Now, determine the relative extrema.
You said like your I equals 0.
Yeah, exactly. The component of this. Yeah. So both 4x plus 8 equals 0 and 2y minus 6 equals 0. So where does that happen?
2x equals -2.
Right.
And y equals 3.
Got it. So that's your point where you have where you potentially have a relative extrema. Okay? X equals -2, y is equal to 3. Now, because we know from looking at this, you have x squareds and y squareds. Okay? Pluses in between that. There's a minus with the y, but not with the leading terms. Okay? This is a z here. That's a paraboloid. Okay? And a paraboloid only has one extrema. That's where it's going to be. And because those are pluses there, it's opening upward. So that's an extreme minimum. Okay? At x equals -2, y is equal to 3. But we also need the z point. So how do we get that? No, that's your z. So at f of -2, 3, this will be your z. I'm going to call it z0. This will be 8 plus 9. Okay. Okay, you're, yeah, I'm just plugging back in here. It's just a little easier. And that would be minus 16, minus 18, plus 20. Okay, so this is your Z0. This is going to be plus 17. That'll be plus 2. That'll be plus 19 minus 16 is 3. So Z0 is equal to 3. Saved by that 20. Okay. So this is a point. Let's see if I can support this now. X equal minus 2, y is equal to plus 3, and z is equal to plus 3. So there it is, and it's opening upward from there. That's your parabola. There is only one relative minimum, and it's also an extreme minimum. Okay, it's an absolute minimum as well. There are no relative maximum. Okay. Now they said by completing the square, why would anyone ever want to do that? But they did.
Well, you got one idiot.
What's that?
You got one idiot.
Let's see.
That was me.
Oh, okay. All right. Well, if you can see that. Okay, I guess what they're saying is
Well, I can explain why I said it, because I was saying complete the square, just read it right off. That was my thinking.
right. Well, I'm trying to see where they're completing. Oh. Okay. Yeah. I see what they're saying now. And that's why when I first read the problem, I said this is one way you can write it. I would never have wanted to write the problem this way. I would have wanted to write it this way. So maybe we're idiots together. I don't know. I would have said 2x squared plus 8x plus y squared minus 6y plus 20 is equal to 0. In fact, I would have put minus 20 on the other side. Okay? And then, yes, completing the square. I was trying to see where they got this. And they kept it on this side, so I'll do that. Okay? And this, by the way, is z. Okay? That's what f of xy is. So this would be 2 times x squared plus 4x blank plus y minus 6y blank, y squared minus 6y blank plus 20 is equal to 0. Well, no. Where did I get the equal 0? There is no equal 0 there. It's just 20. This is your, these are your values. Okay? Now, to complete the square here, add 4. But really what you've done is added 8. 2 times 4. Which would then, you'd have to do a minus 8 here to keep it from changing the problem. And then this would be a plus 9, but because you just added 9, you have to subtract 9, okay? And then this gives you, is that what you said? That gives you your 3. So this is 2 times x plus 2 squared plus y minus 3 squared plus 3 is equal to, plus 3. That's what you get. That's your z. Okay? So this will be at negative 2, 3. That's your xy values. And when x is equal to minus 2 and y is equal to 3, then z would be 3. So that when x equal minus 2, y is equal to 3, z would have to be 3. So that gives you your point. Like you said, that gives it to you directly. Now, what tells you that, I guess, any other x and y you put in here, yeah, it's got to be greater than 3, because this is greater, this is positive, that would be more positive, this would be positive, and this, yeah.
Okay.
Yeah.
No, I didn't get that at first. I was like, why does that tells us the same thing? But I just looked at the x squared and the y squared, and they're both
right
parabolas. And
right, exactly.
It's got to be the minimum.
Yeah, and that's the rationale there, and completing the square just does make it a bit more obvious. I looked at it and said, your leading coefficients are both positive.
Yeah.
That means you're going up. You have nowhere else to go. Okay. So, how are we doing on time? Ooh, we're almost done, aren't we? Do we have time for example 2?
We got 3 minutes.
How much? 3?
3.
3 minutes.
Probably not.
I would think not. I don't think I can read the problem in 3 minutes. So let me put this in place, and let's see what homework exercises we can find. I think you can do any of the odds 3 through 7. They're all at Calc Chat. 7's at Calc View. And we'll pick up second partials test next time. Okay, so between 13.7 and what little we did in 13.8 gives you a little something to work on. Now, we'll finish 13.9 hopefully next time. And then, like I said, we may do a slideshow. No, finish 13.8 next time. I was going to say, where did I get that? And we'll do a slideshow on 13.9, and that's a very short section, and 13.10, Lagrange multipliers, which is a longer section, but not too much longer. And that will finish the chapter. So hopefully we'll finish 13.8 next time, but whether we do or not, I'll try to have your test ready for you, so you will have the weekend that you can work on that. Okay, yes, isn't that exciting? Yeah. And let's see, both of you still have the other test out? Yeah, okay. So don't let them pile up too deep. Okay. Wait a minute.
That might be the other class.
Wait. No. You've turned in your first test. This will be the second test, right?
Yes.
Yeah, you
It's
both
the
test.
other class we have a test out.
Yeah, you have the second test out. Yeah, that's what I was thinking. This is only the second test here. All right, so